Hello, welcome back to LIVENODING. This episode we're gonna take a look at this geometry node setup using simulation zones that's generating something that looks almost like a cellular automaton. So as you can see, I have set up this 5,000 frames, and every frames you can see is kind of like a stars instance that's kind of showing, like popping up and then just disappearing randomly. And if I select them, you can see more clearly. And this is, yeah, I mentioned about Cellular Automaton, and you can read the articles here. This is from Wolfram Math World. So basically, using grid and some kind of rules, you can trickle down or generating this kind of random shapes like a fractal looking pyramid, and the result is like there's all kind of results that's kind of surprising even for Wolfram himself, and it's also similar to this game of life simulations that if you try running it, if you search game of life in Google, it's like a basic ideas is like simulations, and you can actually play here and then start the simulations. So you can basically recreate this inside Blender using simulation nodes. I'm not gonna create cellular automaton. I'm just gonna show you. This is like a simple things that I thought, okay, that looks kind of interesting. But this is actually super simple. Maybe not exactly cellular automaton or game of life. It's just like star that's basically instance on points, but everything is happening inside the simulation zone. So this instance on points is not outside. If I put it outside, the result is going to be completely different than, because this is inside. Every time the geometry being processed in the loop over and over again inside the frame, inside this timeline, we're gonna get this result, okay? Because it's a point, and we instance this star on the points, and then next generations is gonna instance stars on top of the original stars. But I am also randomizing, I think I'm randomizing the delete geometry and also the scale of the star itself. So that's why you get this kind of interesting look. Let me save this first. If I reduce the star to 3 and I get the triangles, okay, we get different result altogether. Let's say, okay, it's just a basic triangles. So you can see sort of a pattern. Okay, it's trying to generate this triangles and on top of the previous points. Maybe I look at it from the top view. But it's happening so fast, and it's just our brain cannot really predict what's gonna happen next. But that's basically, yeah, almost like fractal or cellular automaton. Now I thought interesting, so I want to show you. If I delete it more, we get less triangle. If I delete it less, even if I zero it out, maybe Blender might crash because it's generating too much. It's like, okay, it's like a world population goes too fast, but it will never really reach like a maximum as long we have this deletions somewhere. Yeah, that's why I thought it's a little bit like game of life. Like the human population is like nearly 10 billion, but from a theory it says that it will never reach 10 billion because something's gonna happen causing it to just go down or up, like game of life. But at some point, if something big happens, we might lose everything. Actually, I did run this at some point. I just kept running it. At some point, I think the one that's being spawned maybe too little, and then the one that's being deleted is too much, and then suddenly we get 0 and totally like total 0, and then the simulation stops. So I thought this is a little bit like game of life. It's interesting. I know it's a little bit weird. Just want to show it to you. If we just do it, if we just do this like normally, simulation zone. Previously, if we want to do this instancing, we can start with a star, right? And then we instant on points. It's basically a little bit like this. So we are instancing a star on top of another star, and then we can control the scale, and then we do it over and over again. We can group this or just do it over and over again like that. So it's almost, yeah, it's a fractal looking. Okay, so it's like this, and in fact we can replace this star with one star nodes, and then we can do it this. Yeah, we get something that looks like fractal looking. So let's save this star fractal. I think it can be made more complicated, but maybe my brain is not powerful enough to explain the whole thing, but I want to show you this anyway. You might have seen this type of pattern. The scale can randomize, but you can see this is like a multiple nodes. If you want to do it inside simulation zones, it's simpler, sort of. It's gonna be like this: star, points, instance. Just plug this into the simulation zones. And in this case, we probably need to, we need to use join geometry. Maybe we need to put the star out there, and then geometry goes in. We don't need the input, we just need the star, and then we need to instance some kind of points. We need to generate points and instance the star on top of the points. And maybe we actually need a points over here. Plug this there, so we get a star and we get instance. Maybe over here we realize the instance. Oh, I know where I made a mistake. Okay, it's not like this. We can create a points, and we need to instance the points after we join the geometry. Reset the simulations. There we go. This setup will crash Blender at some point, because it's gonna run out of memory very quickly. It's kind of generating the star too fast. We end up with this fractal, but even like just 7 generations and we already ran out of memory or something. Let's reduce the number. Let's try 3. We get something that look like Zelda triangles, and then it's gonna spawn triangles. We could actually delete the previous one, and then it's gonna get smaller and smaller. Because we specify the scale here, make it smaller. Okay, maybe make it smaller indeed, half the size. Okay, and it gets interesting when we actually delete some of the points, not all of the points, some of the points, using random value, which is Boolean, plug into the selections. Okay, so it's almost like, okay, in this case almost like Wolfram alpha. Okay, we get that. Randomize the seed. Okay, let's trickle down. Maybe we actually need to put a scene time frame into the ID. Now, yeah, we don't actually need to put that into the ID in this case, but it trickles down and it's kind of stopped, but it's actually keep generating behind the scenes. Plug the frame into the seed, maybe. Okay. Now we have something that's a little bit, it's like alive, right? Let's keep generating. As long maybe the big one. Do we need the big one? Oh, the big one stays there. That's why it's keep going. So it's, yeah, that's interesting. What if we have 5? Something completely different. Oh, okay, what you find interesting, because it's like a simulation, right? If you do something after instance on points, like set position, put a random noise or random, I don't know, put noise offset. Yeah, it's gonna spawn. It's gonna shoot. Out. Okay, let's use vector mask minus 0.5 there. Yeah, maybe in this case we can use frame, plug into the W. You can play around with the scale of the noise. It's looking pretty abstract. Don't know if it's really useful or not. Still kind of interesting. At some point maybe there's gonna be like tutorial out there using geometry nodes and simulation input, simulation zone to create game of life, and you can actually, because it's real time, it's and on the fly. That's always the key point, I think. It's real time and also on the fly. You can always change the value. For example, you can click around and then you can generate something based on that. But I think this is as simple as it can get, okay? It can be more complicated, I know. But yeah, it's very much like fractal and very much like game of life. Like explained here, cellular automaton. I don't know, this is probably more complicated. I don't know, maybe it's replacing each one of them. Imagine you're using different instance. Instead of using the star, you use different instance. Each one of the generations will give you different results. So instead of star, maybe different shapes. You can try maybe using string string to curve, string x, plug the instance, right? Different look once again. Play around with this maybe. But the idea is really just you start with a single points and then you instance this whatever curve, star, whatever, and then it's gonna delete and generate. You can try using box. See? Same thing happens. It's like Game of Life. It's a little bit random, but it's fractal like. You don't need this. Maybe you don't need this set position. Once again, fractal things happening. Maybe we don't need this guy. Oh, we need this. So you can use also icosphere. Okay, pretty neat. Maybe, yeah, randomize the scale as well, just to complete this. Plug the frame into the ID and this value of scale, float. Can go into the scale. Okay. It's gonna endlessly reshaping itself. Merge by distance. We can try merge by distance. Oh, maybe don't do that. Okay, I think this is pretty clear, but I want to show you also transform duplicate. Okay, this one. This is probably for the next episode video because it's it's like it's a points that's being pushed around, so it's more like almost like particles. You gotta check out the ErinDale course on like ball simulations made using simulation nodes. It's this is like the basic, like maybe video number 1, but same ideas. Points, generate points. You can turn the points into vertices. Maybe you can later connect the dots. Instance on points, however. And you gotta get something that's like a flocking behavior, but no, it's just like a random points moving in random fashion. Is there's not much control. It can get complicated. And you might lose a bit of hairs while doing this, but yeah, this is what I want to show you. Anyway, there's another one, transform duplicate. Okay, this one. It's simpler, but here we got points, and we are rotating the points using transform geometry, and every time it does the loop, every time the frame updates, it's gonna rotate the points, and then we're simply replacing the points using this icosphere, but you can use anything. So we're basically moving the points in this case instead of deleting the points. So I thought this is kind of interesting for you just to play around with. You can actually try doing this as well. Scene, time, and then random value vector. Plug this frame into the ID, and then this value into the rotation maybe. Okay, now you get something truly bizarre, almost like particle proteins kind of squeezing out from a single point. And let's save this because it's, you can actually duplicate this. It's gonna do the same thing, but the seed, if you pipe it out into the group input, and if you randomize the seed for each one of these, you're gonna get different result. Yeah, I don't know why, but it's interesting. It's really because every frame is changing the ID. That's why we get this weird jerkiness happening. Yeah, but it's a normally you don't want this kind of jerkiness, but it's, I don't know, it's just changing the ID each frame. I thought that's kind of interesting as well. Maybe it's a glitch, or maybe it's part of the feature of geometry nodes simulations. If you actually doesn't want this to be too jerky, you can set the position after join. So turn off this guy. In the offset. Okay. So maybe this is less weird. Still kind of doing it. Turn this off. Okay. There you go. It should be. This is probably what you want. Count 0.1. Okay, yeah. This is pretty much it. This is random walk. This is the proper random walk because we are using a single point, and we loop this in inside the simulation zone with the join geometry. So the last points is being reborn inside the loop, and then we offset the position slightly, and then we can perhaps just do like a deletions or things like that. We can scale the randomness so it's not too random, so it can move just a little bit. Okay, it's pretty cool. It's funny how if we move it while it's already simulating, it's starting to have this kind of motion, extra motion. It's kind of probably glitch, but it's kind of nice. So it's just icosphere. If you don't want the icosphere and you just want to point to vertices, you can do that. And then the next thing what we need is really just connect the dots thing. How do we connect the dots? How do we connect the dots? if I use SVerchok objects in, get our objects, get selection, pause, and then UV connection. I believe this will connect the dot. I think this is supposed to be two video tutorials just put into one. Is this okay? So 3 objects goes in. I need to calculate the translate as well. See? 1, 2, 3. And then we can bake them if you want to, or just use mass viewer. SVerchok is really important, I think. Kind of extension of geometry nodes. You need to install SVerchok separately. It's just another add-on, but as you can see, we can use geometry nodes together with SVerchok, and we can have something that looks like alive. Oh, it's like a trace, like a beat trace add-on using particles, but it's just using geometry nodes. And yeah, I thought that's kind of cool to show you. So if we spawn some random geometry nodes, we can bring it in, and SVerchok will connect the dots. Alright, so that's pretty much it. It's like there's a lot of informations. I know you have to play around with these geometry nodes simulations because just to understand what's really happening, but hopefully you find this useful. Try watching this and then try redoing it yourself, and you will learn by doing it by not just looking at the video. Just try to think what's going on, and then, okay, and then you will figure it out yourself. But basically, using points inside simulation nodes is the right way. You can actually watch the video by Johny Matthews. That's actually really interesting as well, where he didn't actually use instancing. He just used box, and you can spawn box randomly simply by using simulation zone inside geometry nodes. So you can actually just doing that just by plugging the ID and just by using box and transform geometry and then just spawning box on the fly. That's actually really cool as well. So there you go, simulation zone, still kind of mystery. Hopefully you find it useful. Thanks again for tuning in, and I'll see you next time. Thank you. Bye.